Now we were discussing about the doping of uh, doping in semiconductor, and I started to discuss about the donor types doping, where the atoms with periodic table 5 that are doped with semiconductor like silicon or germanium, right? By the way, you have some idea about this doping, na? Intrinsic, extrinsic semiconductor. Do you have?
Yes, sir.
Yes, sir.
Okay. So now your conception is getting clear. If you face any difficulties, then without any hesitation, you put forward to ask me. Okay. So if we now see what I was telling that if we dope with atoms of periodic table 5, then additional electrons that is loosely bound with the atomic nucleus of the doped atom, and as compared to the covalent bonding force, as a result, what happens with very less energy, external energy, it may be thermal energy or external force, the electrons getting free from the atoms, and it is free to move to carry the current. So as a result, what we can see that as a whole, one atom in one particular isolated atom, the number of electrons and number of holes are equal. So that's why as a whole, whenever we are doping the atom like arsenic or phosphorus or antimony, then initially it was neutral, but whenever one electron is getting teared out or escaping from the atom, then this atom is being effectively positively ionized, and this electron is now free to carry the current, the way being the negative charge carriers. Okay, so what we can see now as compared to the number of electrons present for an intrinsic semiconductor in which the carriers are generated only through the generation of electron and hole pair, but here we are getting the electron as a charge carrier without generating the holes. And that's why more number of atoms, addition of the or doping of more atoms will give more electrons as compared to the number of holes in the intrinsic semiconductor as compared to intrinsic semiconductor. So as per the charge neutrality formula, if we consider that Nd0 is the number of doping atom, then this will create the positive ionized atom as Nd plus, plus N in being the number of electron concentration, the electron concentration. Okay. So this is what the this is what the corresponding the for the doping of n-type semiconductor. Okay, doping of n-type semiconductor, and it provides the it donates it donates an electron. Each atom donates an electron, so that's why it is also called donors. And similar things will happen for the germanium also. So now, can you are you getting that how the number of electrons in n-type semiconductor is increasing? So, are you getting it?
Yes, sir.
Okay. So then, in n-type semiconductor, will there be any holes or only it is electron? In N-type semiconductor, will there be any holes or only there is the electron?
So less holes.
Yes,
Less holes.
less. Why it is less?
Because they would be made only by the means silicon means the doping will have
And
electrons.
how electron hole pairs will be generated?
Sir, only if a valence electron gets dislocated from the bond.
Valence bonding electrons,
Yes, yes.
covalent bonding electron, right? Yes. Just try to understand here. Always there will be electron hole. Always there will be hole. But here, as the covalent bonding force is, the electrons are bound with the covalent bonding force, so the number of electrons or electron hole pair generation is much less as compared to the electrons donated by the donor atoms. Say, for example, in intrinsic semiconductor, the electron concentration, the intrinsic electron concentration Ni is equal to Pi, because in intrinsic semiconductor, the electrons and holes are generated in pairwise. So that's why the number of electrons and holes are equal. Say if we consider it is N0, then this is given by 1.5, it can be calculated, is equal to 1.5 into 10 to the power 10 per cc, that means per unit volume. Okay. Now, if we dope the silicon with number of atoms per unit volume as, say, in the order of 10 to the power 14 or 10 to the power 15. Now, if all the atoms are ionized, then try to understand the difference. Though this 10 to the power 10 number, this is very large, but as compared to 10 to the power 15 or 10 to the power 14, this number is very less. So that's why the number of electrons, if you consider the total number of electrons and the total number of holes, now as compared to this, if all the donor atoms donate the electrons, the number of electrons becomes more as compared to the number of electrons generated due to electron hole pairs. Is it clear? So that's why the both electrons are and holes are there, because there is always, due to finite temperature, there will be breaking of some covalent bonding, and due to that the electron and hole pair will be generated pairwise, and this mechanism will be always there to provide the electron hole pair. Okay. So this mechanism will be always there in any both intrinsic and extrinsic semiconductor, but for extrinsic semiconductor, as the number of atoms are more, so that are giving providing the more electrons or more charge carriers to the atoms. Similarly, for the acceptor types atoms, acceptor types, if we consider one atom with periodic table from periodic table 3, that is with valence 3 valence electron, like boron, aluminium. If we add into the silicon of group 4, if we add, then what will happen? What will happen? Similar to this, there will be a shortage of 1 electrons, right? And due to that shortage of electron, there will be the tendency to accept an electrons. So that's why it is known as the acceptor types atom doping, and these are called the acceptors. And here, as you can see here, uh, the each atoms provides one holes, that is one vacant state. So accordingly, the acceptor types atoms provide more holes as compared to the electrons, and whenever it accepts an electron, what would be the ionization? It would be negative. If it accepts an electron, what would be its ionization? Positive or negative?
Negative.
So there's effectively it will be negatively ionized, right? Negatively ionized. So donor types atoms, by donating an electrons, it is getting positively ionized. Acceptor types atoms, after accepting an electrons, it is getting negatively ionized. Okay, so accordingly, whenever it accepts an electrons, so one covalent bond, like look at this here, it has tendency, so always it is providing an holes. So number of doping, depending on the number of dopings, you are increasing the number of holes. Okay. So now in a system like this, if you consider, so far we are considering the current due to the electrons and holes only, but there is also the positively charged ionized atoms, negatively charged ionized atoms. So will they contribute any current? Can you tell me?
No, sir.
Don't be confused. Some of the students getting confused and this confused with the electron holes as well as the positive and negatively ionized atom. Will they contribute?
No, sir.
Why?
They cannot. They are not mobile. I guess they
They
cannot
are
move.
not mobile. Why they are not mobile?
They are bonded to
Bonded.
some other
Only
atom.
due to bonding. Bonded, that's why. Or there is any other reason?
Their size matters.
Not size, it is actually mass, weight. Just like if you want to throw a teeny stone, a small stone, whereas if you want to move one big wall, okay, if you apply your force, like and if you alone want to you apply your force with to a wall, then what will happen? You cannot move it like this, whereas you can easily move or throw any small stone. So similar to this, the mass of the electron is very less as compared to the mass of the atoms. That is consisting of the nucleus, proton, and effectively all of its mass is within the ionized atoms. So that's why these are called the immobile ionized atoms, and this cannot be movable. You cannot move it. These are stationary. Okay. So that's why you don't be confused. These ionized atoms, both for the donors as well as acceptors, these are not carrying any current, and the current will get only due to electrons and holes. Now the next question is the electron. Okay, the electron we know that it is the free electrons. It is moving and it is giving the current. Now the holes, that is one vacant state. How it provides the current? How it provides the current? Okay, let us try to understand. Okay. See, for let us just you think about this, see this diagram and try to understand here. Uh, Look at this. There is a vacant state. Now, due to at finite temperature, as this vacant state has the tendency to accept one electron. So what happens? If somehow from nearby one covalent bond is breaking, then a electron hole pair will be generated, or it has the tendency to accept an electrons from another covalent bonding. So as a result, whenever these electrons will be jumping from here to here, then the covalent bond will be created here, then the vacant state will be created here. Similarly, if you consider here, there is another covalent bonding, and also the electron is coming from here, and here another vacant state is created. Okay, now just try to understand here the whenever the electrons are this due to filling of this vacant state with the electrons, now the holes positions are moving opposite to the electron. This is hole position is moving opposite to the electron. Now effectively what you can see that the vacant state is moving opposite to the direction of the electrons, and as such the positive charge that is here, if you consider the electron as the negative charge, and as such it is the positive charge moving in the opposite direction. So in that way effectively you are getting the we are getting the current around the direction of the opposite to the direction of the electron movement. So in that way, the holes also contribute the current. Okay. So this is now more number of electrons and holes, you will get the more current, and you will increase the conductivity. That also will see how depending on the number of carriers, the conductivity can be increased. Okay. So now let us start from here. How the number of electrons, how many number of electrons will be there in intrinsic semiconductor and extrinsic semiconductor, and what is the relationship between the Fermi energy and band gap. So this is what the relation. This derivation can be derived. This formula can be derived. Okay, this is what the N0 is the number of electrons. Number of electrons for in one intrinsic semiconductor. That means in the conduction band. As already we have seen the probability distribution function, the Fermi-Dirac probability distribution function, where we define the probability of occupancy of an electrons as per the Fermi-Dirac statistics that is given by this formula that already we have seen. Oh, we want to find out from that point of view, this is what is known as the energy state density. That is, NC defines the number of available allowable energy states per unit value. What I told, what is NC? What is NC? Number of allowable energy states per unit volume in the conduction band. Okay, and if we multiply it with the number of with the probability distribution function, if we multiply it, this indicates the number of allowable energy states multiplied with its probability of occupancy gives the number of electrons at that energy band per unit volume. Okay, so accordingly, this is the formula to get the number of electrons at a particular energy states, and it is given by N0 is equal to Nc e to the power exponential minus Ec minus Ef by kBt. Kb is the Boltzmann constant, Ec is the conduction energy level, Ef is the Fermi energy level. So, and her NC is the energy state distribution function. This is a state density and is given by 2 into 2 pi mn effective. This is the effective mass of the electron, kBt whole to the power 3 by 2 h cube. This can be derived. Okay, just for your information, I am telling you. Just you will remember, this is how effectively we can calculate the number of electrons in a particular energy band. Here the formula is used, EC is used if it at any other energy states we consider allowable energy states. Also at that energy level, what would be the number of electrons per unit volume, that also we can calculate in the similar way. Okay. So similarly, P0, the number of holes, this is, now look at this here, the EF the Fermi-Dirac distribution function, that is, if we consider this diagram here, here, this is the Fermi energy, okay? And if we move further from the Fermi energy, we move, if we move away from the Fermi energy, that what does it indicate? That means it is away from the Fermi energy. That means energy level is more, and the probability of the electrons is getting less. So if we move away from the Fermi energy, the probability of the occupancy of an electron is getting less. Similarly, if we move towards the left side, that is, if we go towards the less energy level with respect to the Fermi energy level, the number of vacant state, look at this here, the number of vacant state that is mostly resided in the top of the valence band. And if we move further from the Fermi energy, the number of, as we can see here, this is E minus exponential E minus EF by KT. Okay, so if we move further away from the this away, this is the formula, away from the uh, 1 divided by, yes, this is the formula, away from the Fermi energy level, the number of holes also getting decreased, also decreases. Are you getting it?
Yes, sir.
This indicates what? That if you consider here the number of holes, that indicates in the valence band, that is EV, and how it the difference from how far it from the Fermi energy. This is EF minus EV exponential term, and NV again. This is the number of allowable energy states per unit volume in the valence band, and this gives the number of holes in the valence band. Higher NV is given by the same expression with only with difference. It is effective mass of the holes. Okay, or proton. This is what the corresponding the number of holes. And as for intrinsic semiconductor, the electrons and holes are generated pairwise. That's why only for intrinsic semiconductor there is no other way of getting electron and holes. So if you consider this is electron, this is hole created in the valence band. So always it will be generated in pairwise. That's why the number of electrons and holes are equal. So if we make this equal as per this formula, we can make equate it, and then we can solve for the Fermi energy in terms of the effective mass of the electrons and holes and all other constant. So that this is your home task to solve for the Fermi energy. Okay. So similarly, if we see the NP are in the equal to N0, N0 is equal to P0 is equal to, say, if I write that it is Ni, this is what Ni is. Just a minute. It's not the same. Yes. If we consider N0 is equal to Ni, then Ni square is equal to N0 P0. That is the product of these two. This is just if we to multiply this and this, then we will get this expression, and which indicates that it is Ni square, that is the intrinsic semiconductor electron concentration in the electron or hole concentration in the intrinsic semiconductor is depends on what? The band gap, and it depends on the temperature also. Is it clear? So what you can see that this temperature, if the band gap is more than the number of electrons also will be less. Okay. Also, if you see, if you see here that if you increase temperature from this expression, you can see if you increase temperature, what you can see, if you increase temperature, uh, it will increase the number of electron or decrease the number of electron.
Increase.
Decrease.
If we increase it, then this term will be less. Accordingly, it would be increasing the number of electrons, right?
Yes, sir.
Yes, sir.
So this is how the dependency of the electrons, number of carrier generation with band gap and temperature. So as per the charge neutrality formula, now for extrinsic semiconductor, what we have seen that if we donate some extrinsic atom like donor atoms or acceptor atoms, then what will happen? The donor atom will be positively ionized and it will give the electrons, and acceptor atoms will accept an electrons and negatively ionized. Now, if you consider in a semiconductor, both donors and acceptors are present, then as per the charge neutrality formula, because all the atoms as a whole, it is neutral, though it consists of both electrons, positive and negative charge carriers or ions, but it is as a whole, it is neutral. So that's why it must follow the charge neutrality formula. That means effectively, if we consider we know that electron is positively ionized carriers. So holes, if we consider here the positively ionized carriers, then the total charge, positive and negative, that would be equal. So accordingly, whatever the number of holes, okay, generated within the semiconductor, that plus the positive ions, that is the Nd plus. Nd plus means the donor atoms donating an electrons getting the positively ionized. That should be equal to the number of electrons plus the number of acceptor ions, that is negatively ionized acceptor atoms. This is what the charge neutrality formula. Okay. And here N and P, is it the intrinsic charge carriers? That means the number of electrons, electron density and the hole density. This NP is same as Ni, or P is same as Pi, or it will be different. Tell me.
Sir, can you please repeat the question?
And what is this charge neutrality formula? Do you understand?
Yes, yes.
Okay. In charge neutrality formula, N and P represent the electron concentration and hole concentration. And this electron concentration, whenever we are, that is for the semiconductor in presence of doping, or the presence of some extrinsic semiconductor where both donor and acceptor atoms are present. And this is the charge neutrality formula. Now my question is, this N and P would be same as the Ni or Pi, because Ni and Pi is the electron and hole concentration for intrinsic semiconductor. Will these two be same or it would be different?
No, sir, it would be different.
Different, sir.
Yes.
Yes, sir, different.
It would be different. Then the question is, how many number of electrons and holes would be there due to the generation of the electrons, due to the doping, that means adding some extrinsic semiconductor. Okay, extrinsic atoms. So if we consider a donor types atoms are present, then due to the generation of the electrons, how it will affect on the holes or whether it will affect or not. So far, I told you that addition of electrons, addition of donor atoms in a semiconductor will provide electron or will donate the electron. That means it will increase the number of electrons. So that will affect on number of holes, that is intrinsically generated holes or not. That let us try to understand. Okay. Are you getting my question?
Yes, sir.
Okay. So here definitely it will affect the number of holes and how it will be affected. Now let us try to understand. Again, if we consider that extrinsic semiconductor, the band diagram for the extrinsic semiconductor, just let me start from here, then it will be easier to understand. So if we consider a separate piece of p-type semiconductor and n-type semiconductor, that I'm not defining the what is p-type and n-type semiconductor. I'm assuming that you know a little bit about this. That's why, and you know that whenever the p-type acceptor types atoms are doped with the silicon or germanium, then it provides the more holes carriers, and that's why it is called the p-type semiconductor. Whereas for n-type semiconductor, the donor types atoms, that is the atoms of periodic table 5s, are doped doped with the silicon or germanium, and then it will donate the electrons, and here the more number of electrons carriers are there as compared to holes. That's why it is called n-type semiconductor. So that you know, that's why I'm not going much details there. Okay. Now, if we consider that for p-type semiconductor, what would be the position of Fermi energy? Or what will there be any change in the Fermi energy level, or there if changes, then what would be the changes? So for p-type semiconductor, this EI represent the Fermi energy for intrinsic semiconductor. EC represent the conduction band energy level. EV represent the valence band, top of the valence band energy. EC represent the bottom of the conduction band energy. Then what would be the change in Fermi energy? How can we explain? Well, again, you have to remember that the significance of Fermi energy. That is the energy level at which you can consider both the equal probability of electron and holes are there. Okay. So now, if you consider the p-type semiconductor, what does it indicate for p-type semiconductor? For p-type semiconductor, what does it indicate? P-type semiconductor, you tell me. In p-type semiconductor, can you hear me?
Yes, sir.
Yes, sir.
In p-type semiconductor, which carriers are more?
Holes.
What type of carriers are more?
They are
Mostly,
holes.
which type of carriers are there?
Positive carriers.
Positive means what? Here we will define two carriers. We have defined electrons and holes. Electrons and negative carriers, that is available due to two ways in semiconductor. One is either electron hole pair generation due to the breaking of covalent bonding. Another is due to the addition of some extrinsic semiconductor. It is provided by that extrinsic atoms and loosely bound electrons it is providing, or it can have the capability to accept an electrons. So for p-type, it can accept an electrons that provides an additional holes, and for n-type it gives the electrons. So for n-type, the mostly it is the electron carriers, and for p-type it is holes. Now, if we consider intrinsic semiconductor, You tell me in the valence band what are there. It is valence band and it is conduction band. You tell me in the valence band which type of carriers are there and what are there in the conduction band what are there for intrinsic semiconductor. You tell for intrinsic semiconductor what would happen if there is a whole generation of if one electron jumps from the valence to conduction band. What does it indicate? This jumps from valence to conduction band. What does it indicate? This indicates that this is the energy gap Eg, and this amount of energy is required to break the covalent bonding. Are you
Yes,
getting
sir.
my point?
Yes, sir.
Okay.
Yes, sir.
Actually, what happens if you see here, all the electrons are bonded with covalent bonding. It is now it is jumping from valence to conduction, and this indicates that the amount of energy required to break the covalent bonding. So accordingly, this is the diagram. This indicates how from valence band electrons jumping to conduction band. And here one holes is created. Holes is created. What does it means? That means a vacant state is created in the covalent bond. Okay, and this electron is moving here and there. Is it okay? Just like if you consider in your house, there is separate 10 box to keep 10 balls. Now you are taking one balls to play, then one place is empty. So in the field box, there is one empty place where you can play, keep any one balls. Okay, so if you shake it, then any one of the ball can play, can field with that position. Are you getting my points? And what the balls you have taken out, that you can play, you are taking and playing anywhere. Similarly, this electrons is jumping to the conduction band. It can move anywhere, and this also in the vacant state, it can be filled by another electrons from nearby vacant state. Anyway, always there will be one vacant state, and similarly, the electrons and holes pairs will be generated equally. And as the equal number of electrons and holes are there, so its position must be in between at the center for intrinsic semiconductor to get the equal probability, that is half. Are you getting it?
Yes, sir.
Okay. So now you can just imagine about the p-type semiconductor. In p-type semiconductor, what you are getting? Actually, you are by doping with extrinsic atoms, that is aluminum or boron, we are actually we are creating some additional holes in the valence band. We are actually creating some holes here. Okay, and creating some holes, what does it indicate? This is all the electrons are still in the valence band energy state. So in the valence band, there already there is some vacant state is there already. Not all the electrons are completely filled. If all these are completely filled, then in the valence band all the allowable energy states are completely filled. But there is some energy states. That means we are creating some allowable energy states in the valence band, and that allowable energy states are empty still. Is it clear? Okay. Are you getting it?
Yes, sir.
Okay. So now, as any finite temperature, also some of the covalent bond may be may be broken. In that case, another electron hole pair will be generated. That means the electron can jump into the valence band. Any covalent bond breaking, that means it is crossing the band gap. Are you getting it? Is it clear? Clear to you?
Sir,
Yes, sir.
this thing please repeat a bit.
Repeat. Okay. See, whenever we are doping some acceptor atoms, what we are doing? We are providing some vacant state. Acceptor atom
Yes,
means what? There is some deficiency of one electrons. That means
yes,
to make complete the covalent bonding. So what does it indicate? That means there is additional one, each atom providing one vacant state, right? So that
Yes.
means one holes you are providing. And this is actually basically in terms of energy level, what we are doing in the valence band, we are creating additional energy states in the valence band where there is no electron. So whenever in addition to the number of electrons completely filled by the uh, electrons, if you create additional energy states within that, then there is no electrons. That means the vacant state is created. Is it clear? And
Yes, sir.
also due to temperature, some of the electrons may get sufficient energy which is greater than the band gap energy, or some covalent bond may be broken due to vibration of the atoms, right? Accordingly, the electrons from here will jump to the breaking of the covalent bonding. That means the uh, uh, energy is greater than the band gap energy and it will jump here, right? So this is what the number of holes now more in the valence band as compared to the number of electrons in the conduction band. So now to make equal probability in the of the Fermi energy with respect to the electron and holes, to make 50%, what you have to do? Are you getting it?
Yes, sir.
Then towards which direction the
Yes.
Fermi energy must be shifted?
Towards I mean, valence bond energy, valence bond side
Yes,
to reduce it.
yes. So this difference indicate what? The number of electrons is getting less in the conduction band, and more close to the valence band, it indicates more holes are there in the valence band. Okay, closely the that is, and this spacing, that is the position of the Fermi energy, is very important to identify or to get an idea that how much electrons are there or how much holes are there in the valence band and conduction band. Okay, so that's why in p-type semiconductor, the position of the Fermi energy will be closer to the valence band energy level. Okay, and position of the similarly, if you consider n-type semiconductor, what would happen? It is creating additional electron, so it is providing more electrons as compared to the number of holes jumping from the valence band to the conduction band, because already it is completely filled, the valence band is completely filled here. Okay, and this is already here in the conduction band, more electrons are there already here. Is it okay? Are you getting it? So
Yes, sir.
then only holes will be generated when the covalent bond will be breaking, and this will be generated due to it will be pairwise, it will be generated and jumping here, it will be pairwise generated jumping here, whereas more additional electrons are already there. This is what in the conduction band. Okay, and this is what actually the more electrons are there in the conduction band. And the Fermi energy now, what would be the position of the Fermi energy? So to make it justifiable as per the probability distribution function, the Fermi energy must be shifted towards the conduction band energy. Okay, and so that this is where the important point to be noted here for donor types. For n-type semiconductor, the Fermi energy is close to conduction band energy. For p-type semiconductor, the Fermi energy is close to valence band energy. Okay, is it clear?
Yes,
Are
sir.
you
Yes, sir.
okay? Here, another thing, let me introduce here in the, so far I am talking about the Fermi energy, conduction band, valence band energy. Now, how I will justify with respect to the valence band these acceptor atoms and the donor types atoms? what happens? Look at this. Already I told you that for the donor types atoms, the electrons are loosely bound with the atoms, with the nucleus. As per the Coulombic force, it is loosely bound with the electrons. Actually, if we consider this is the valence energy, this is the conduction band energy, bottom of the conduction band energy. And for extrinsic semiconductor, already we defined and we have seen that the Fermi energy is close to valence conduction band energy. This is Fermi energy. Okay, this is. Actually, what happens? This energy, which is required to tear out the or loosely bound energy level, this indicates that what it is just below the conduction band level. Another energy level we are producing here known as the donor energy level in the band diagram at which these electrons are residing. Okay, that is the donor types the electrons in the donor types atoms are residing. Now look at this. As the donor types electrons in the donor types atoms are residing here in this energy level. So with very small external energy, it can jump here easily as compared to the covalent bonding, breaking of the covalent bonding from the valence band to the conduction band. So that's why it is more easily jumping and all the donor atoms are providing the electrons to the conduction band. This is the explanation in terms of the band diagram. Okay, all the things you should understand clearly that so that you can explain it properly. What I told, can you understand?
Yes, sir.
Okay. Similarly, can you tell what would be the position of the acceptor energy atom, acceptor level? What may be the position? Just you guess.
It is near valence energy level.
Good. Good. It is near to valence energy level. Just I am trying here. Okay. Because with very small energy, it has the uh, tendency to accept or it can accept the electrons. Okay, look at this here. So as it is close to it is what is known as acceptor energy level. As it is very close to the valence band, now electrons can easily jump from here to here and it can accept the electrons. Look at this here. As compared to the electrons jumping to this conduction band. Are you getting it?
Yes, sir.
Okay, so what we are doing, that means the doping doping of the atoms. Uh, Actually, we are creating some additional allowable energy states within the forbidden band. So, for example, here ED, the donor energy level is created within the funnel just below the conduction band, and acceptor energy level is created just above the valence band. Okay. Now just so far I told you that just one more things I'll explain today. The transport phenomena that I told you. This is what the relationship. Sorry, just let me tell you here where we were. Uh, Now, if we consider what we have seen that with the addition of donor and acceptor atoms in the semiconductor, the Fermi energy position is shifted, not it is fixed, remains same as for the intrinsic semiconductor. For donor types atoms, it is N-type semiconductor, it is shifted towards the conduction band. For acceptor or P-types semiconductor, it is moved towards the valence band. Right? Are you getting, all of you are getting it?
Yes, sir.
Yes,
Okay,
sir.
Okay. So then also as per the previous formula, we can calculate the number of holes and number of electrons in the valence and conduction band in one extrinsic semiconductor as per the position of the Fermi energy and the valence band energy. Now, as the Fermi energy position is shifting, so accordingly it will determine the corresponding number of electrons and holes in terms of the energy state density. Okay, so accordingly, if we consider P and N is the number of electrons, number of holes and number of electrons, as per the present Fermi energy position, then it can be obtained by using this formula. And accordingly, what we are getting, it depends on the difference between EC minus EV, that is the again the band gap, and the temperature, right? So there's the band gap remains same at a particular temperature. So what does it indicate? It indicates that the product of the number of electron and hole concentration in an extrinsic semiconductor remains same. And again, EC minus EV is EG. And also this is same as in I square, already we have seen. So this indicates that NP is equal to Ni square. This formula is known as mass action law. It is known as mass action law. Okay. What does it indicate? What is the statement? In extrinsic semiconductor, the product of the concentration of electron and holes are same and which equal to the square of the uh, concentration of intrinsic. Okay, is it clear?
Yes, sir.
Yes, sir.
So then, if we consider now for intrinsic semiconductor, external doping concentration becomes 0, then N0 P0 is equal to Ni, which is equal to a product is Ni square. Now for extrinsic for N-type semiconductor, the doping concentration is more as compared to the acceptor types atoms. For N-type semiconductor, effectively doping concentration is much more. So accordingly, as it is very, very greater than this acceptor atom, so the difference is also very, very greater than this, and this is very greater than the intrinsic semiconductor, intrinsic concentration. So accordingly, what we will get that N0, that is what the N0 is very closely equal to ND total if we consider that is the doping concentration. Then as NP is equal to Ni square, then what we'll get? We can get the whole concentration as Ni square by Nd. That means if we increase the more electrons, the holes will be decreased by this factor. Are you getting it? Similarly, for acceptor types atoms or the p-type semiconductor, if the acceptor atoms is much more as compared to the intrinsic semiconductor, then we can get the electron concentration will be reduced by this factor Ni square by Na. Okay, this is obtained by as per the mass action law. Okay.
Yes, sir.
Yes.
Okay, just another 2 minutes I'll take to explain how it depends on why we need to increase and what is the most important
Uh,
things of doping. Bolo? Or I'll explain it in the next class. अच्छा ठीक है, let me leave it today. In the next class we'll explain it and we'll start from here. ठीक है?
Okay, sir.
Okay, sir.
Okay.
okay, sir.
Okay, I'll share the PPT in MS Teams in the link. There will be a folder, class materials and lecture PPT. You can find it. I'll share it. Okay.
Okay, sir. Hmm.
Okay, so do you have any queries?
Sir, I have one.
Bolo.
Sir, in a certain slide, there are some marking on conduction band and valence band.
Yes.
Please roll it up. No, sir, down. Maybe. The topic was probably how many electrons or holes are in these bonds.
How?
How many electrons or holes are in these bonds? Probably the topic was this.
This one? This one? This one?
This one,
Yeah.
sir. This.
Yes, yes. Bolo.
Sir, why there are some markings on conduction band and valence band?
Okay, okay, okay. This
What
is
does it?
what, whenever look at this here, this indicates for intrinsic semiconductor. If you see here, some of this indicates what that the equal number of the look at this empty states as it is defined without any color. This same color represent that in the valence band these are initially the completely filled by the electrons. And here, this now the number of electrons in the conduction band, whatever the number of electrons in the conduction band, that will remain same as the number of electrons leaving from the valence band, right? And to indicate that, look at this, this size of this color indicates that equal number of electrons and holes are jumping from valence to conduction band. Okay.
Okay,
That's
sir.
why this area or volume is equal.
Okay. And sir, what is
Uh,
this EFF?
and also jumping the electrons, so what happens? First, it will start to fill from the lower energy, and it is assumed that it is starting to fill the conduction and lower energy states, and that's why it is indicated like this. And also, the electron will jump from the top of the valence band energy states, and accordingly, top of this sum of the energy states are empty as indicated here. Bolo?
Sir, what is this EFF here in the equation of NC and NV?
EF. EF is the
EF.
Fermi energy.
Okay.
EF is the Fermi energy, and this EMN effective. This is the effective mass of the electron. This is effective mass of the holes. EC is the conduction band, bottom of the conduction band energy. EV is the bottom, top of the valence band energy. NC is the energy state density in the conduction band, and NV is the energy state density in the valence band. Okay?
Okay, sir. Thank you.
Okay. Okay, so ठीक है. If you don't have any other queries, then let me stop here. I'll share some problem as a home task. We'll solve it based on the theory so far I taught. And